Welcome. This is now video number 10 on the construction of hyperreal numbers. I am going to start with a quick intro on hypernatural numbers and move on to understand summation over star n. You probably remember that n is a subset of star n and that all elements which are in star n but not in n are unlimited. In star n, we can find many copies of Z. Such copies are centered around a hypernatural number n, and we write it gamma of n. And it is simply given by the set of all elements of the form capital N plus n with small n in Z. I guess I should have been adding a star here if I wanted to remain absolutely consistent with the notations I've introduced so far. All the elements in gamma are unlimited and they follow the ordering which is imposed by the elements of Z. Gamma n can alternatively be expressed as a set of hypernatural numbers k which are limited distance apart from n, or as the intersection of star n with the galaxy of k. We call gamma of n the star n galaxy. We can verify that gamma of 2 is the set of integer z, and you will find more details in the book of Goldblatt, such as how to define an order between the star n galaxy, the fact that there is no greatest or smallest galaxies, and that there is always more star n galaxy between any two galaxies. Now I wish to focus on extending the summation over the hyperreal numbers. Let me start with the simplest sum, the sum from 1 to n of 1. What troubled me at first is that addition is a closed binary operation on n, so I can keep adding 1 for as long as I want. I will never get out of the natural numbers. So if this sum here means anything, where n is a unlimited hyperintegers, how do I jump from n to star n? To understand this, I propose we look at the hypernatural number n defined by the increasing sequence here. I am now going to replace n by the function gn, which is the sum from 1 to n of 1. I can therefore rewrite n like this, which we know from our previous lecture can be written as the action of a constant sequence g on an increasing sequence 1, 2, up to n, and so on. In other words, this is the extension of g acting on n. Since g was the sum of 1 from 1 to n, we are going to write the extension of g as the sum of star 1 from star 1 to big N. So now we have two equalities. Let us see how the second one allows us to recover the first. Assume we are running the sum from star 1 to star n, which we know to be the extension of an integer. This is clearly star 1 summed up n times, and therefore it is equal to star n. Alternatively, I could write the sum using the function g we had previously defined, and we remember the contraction of the two stars that is going to simply lead to star n. We can conclude that adding star 1 a limited number of times is going to give us a limited number, but if we add star 1 an unlimited number of times, we get an unlimited number. Let us now look at the hyperreal number n times n plus 1 over 2. Each element of the sequence can be written as a sum here, which once again I'm going to call g, so that we have n times n plus 1 over 2 equal to the extension of g acting on n. Replacing g by the sum, we get the Gauss summation formula extended to hypernatural numbers. If I choose to sum up to a limited number n, again we have the contraction of the stars that is bringing us back to the formula for integers. And alternatively, if we write the sum explicitly, we can define a change of variable with j equals star k, which again brings us back to the expected formula for integers. So finally, we are now in a position to understand the more general case. Let k and q be two natural integers and f be a hyperfunction from star n to r. Then the sum of fj from k to q is a hyperreal number given by the equivalence class of the sequence of sums of f and j running from kn to qn, where kn, qn, and fn are the elements of the sequences defining k, q, and f.